Hey everyone, welcome. Today we're tackling Leetcode problem 3342. Find minimum time to reach last room 2. It sounds like an adventure, and it is. We'll break it down step by step, so no worries if it seems tricky at first. Let's get started. Alright, so here's the setup. We're in a dungeon, which is basically a grid of rooms. We start at the top left room, 0, 0 at time 0. Our goal? Reach the bottom right room, N1, M1, as quickly as possible. Now, the tricky parts. First, each room has a move time. This value is the earliest time you can start moving to that specific room, I, So, if you're about to enter a room, you might need to wait if your planned arrival is too early. Second, moving between adjacent rooms, up, down, left or right, has a cost that alternates. The very first move you make costs 1 second, the second move costs 2 seconds. The third move costs 1 second again, and so on. It keeps switching between 1 and 2 seconds. We need to find the absolute minimum time to arrive at that final room. Let's walk through the first example. Imagine move time is fix meis to mebre that than fixil e0 4 helvi. We want to get to room 1 4 helvi fix ban at 6 ban 4 frichindiv doncha fix ban frichindiv donner 0 1 4 his ban mebrun 6 bix vix ban 1 we're 0 at time 0. We've made 0 moves. Okay, let's try to go from 0 0 to 1 0. This will be our first move. The cost for the first move is 1 second. Now the room 1 0 has a move time of 4. This means we can only start our journey towards 1 0 at time 4 at the earliest. Our current time at 0 0 is 0. So the actual time we begin this move is the maximum of our current time, 0, and the move time of the room we're going to, which is 4. So max, 0 4, equals 4. We start moving at time 4. The move takes 1 second, so we arrive at 1 0. At time 4, plus 1 equals 5. Great, we're at 1 0 and the time is 5. We've made 1 move so far. Next let's go from 1 0 to 1 1. This will be our second move. The cost for the second move is 2 seconds. The room, 1 1, has a move time of 4. So the time we can start this journey towards 1 1 is max, current underscore time underscore at underscore 1 0, move time underscore for underscore 1 1. That's max, 5 4 equals 5. We start moving at time 5. This move takes 2 seconds, so we arrive at 1 1 at time 5 plus 2 equals 7. And that's our answer for this example, 7 seconds. This matches the example's explanation. Okay, so when we see minimum time or shortest path on a grid, what usually comes to mind? For me, it's often Dijkstra's algorithm. It's really good at finding the shortest path when edge weights, move costs, are non-negative. But our state isn't just our current room, row, column. The cost to move depends on how many moves we've already made. So our Dijkstra state will need to include the current time, our current room, and the number of moves made to get there. This is because the number of moves tells us if the next move costs 1 second or 2. So let's refine that. We'll use Dijkstra's. The items in our priority queue will be tuples representing the state. Current underscore arrival underscore time, row, column, number underscore of underscore moves underscore made. The queue will always give us the state with the smallest arrival time. We'll also need a way to keep track of the minimum time found so far to reach each cell, considering the move count. Let's use a 3D array, say min underscore times, column parity. The parity part, 0 for even, 1 for odd number of moves, is because the next move's cost depends on whether we've made an even or odd number of moves. So min underscore times b to lock and frings be the fastest way to get to respite using an even number of moves. Now for the heart of the logic. Suppose we've just processed a state. We arrived at room, call mass, at current underscore arrival underscore time, and it took us k moves. First, figure out the cost for the next move, the k plus 1 th move. If k, the number of moves already made, is even, this new move will cost 1 second. If k is odd, it'll cost 2 seconds. Then, for each valid neighbor, nc of our current room, we need to determine when we can actually start moving towards this neighbor. Remember, we can't start heading to Walab Mekan C before it's move time, Also, we can't start before we've even arrived at our current cell. So the time underscore to underscore initiate underscore this underscore move will be the maximum of our current underscore arrival underscore time at correct near C and move time C. Once we know when we start that motion, the arrival underscore time underscore at underscore neighbor is simply that time underscore to underscore initiate underscore this underscore move, plus the cost underscore of underscore next underscore move we just calculated. The new state for the neighbor will then be arrival underscore at underscore neighbor, na ya, nc, k plus 1 underscore moves. We'd add this to our priority queue if it's a better path to nrnc with k plus 1 moves. Alright, here's the Python code that puts all these ideas together. It might look a bit dense at first, but we'll walk through the key parts. The core is Dijkstra's algorithm using a min priority queue. First up, we get the grid dimensions, n rows and m columns. Then, min underscore arrival underscore times is that 3D list we talked about. It stores the minimum time to reach cell e to it, having made an even number of moves at index 0 for the last dimension, or an odd number of moves at index 1. We initialize all these times to infinity. Our priority queue, PQ, starts with one entry, 0, 0, 0, 0, 0. This means we're at cell 0, 0, arrived at time 0, having made 0 moves. And of course, we record that min underscore arrival underscore time 0, 0, 0 for 0 moves, which is even, is 0. Now, we enter the main Dijkstra loop. As long as there are states in our priority queue PQ to explore, we pop the state with the smallest time underscore cur. This gives us the current arrival time, the cell, b pop the c, and the number of moves k underscore moves taken to get here. The first if is a standard Dijkstra optimization. If we've already found a faster way to reach this cell with this move parity, k underscore moves %2, we can skip this one. The second if checks if we've reached the destination, n1, m1. If so, because Dijkstra always processes the shortest paths first, this time underscore a air underscore cur must be the minimum time. We can just return it. Next, we figure out the cost for the next step. If k underscore moves, the number of moves made so far, is even, then this upcoming move, the k underscore moves, plus 1-th move, costs 1 second. Otherwise, it costs 2 seconds. Then we loop through all 4 possible neighbors, right, left, down, up. For each potential neighbor, nrnc, we first check if it's actually within the grid boundaries. This is where our key rule comes in. The time underscore to underscore initiate underscore move towards the neighbor, na nc, is the maximum of our current arrival time, time underscore r underscore cur, and the move time specified for that neighbor cell move time, do. We have to respect that move time gate for the neighbor. Once we know when we can start moving, the actual time underscore arr underscore neighbor is that initiation time, plus the cost underscore for underscore next underscore move. The number of moves to reach this neighbor will be next underscore k underscore moves, which is just k underscore moves plus 1. Finally, if this time underscore ar underscore neighbor is better, less, than any previously recorded time to reach, with next underscore k underscore moves parity, we update our min underscore arrival underscore times table and push this new, better state onto the priority queue for later exploration. So how efficient is this solution? For time complexity, the number of states we can have is roughly the number of cells, n times m times 2, for move parity. Each state is pushed onto and popped from the priority queue at most once. A priority queue operation, like push or pop, takes logarithmic time, proportional to the number of items in the queue. So the time complexity is roughly n times m times log n times m. For space complexity, the min underscore arrival underscore times table takes n times m times 2 space. The priority queue, in the worst case, might hold a significant portion of the states, so space complexity is order of n times m. This is pretty standard for Dijkstra on a grid. So, to sum it all up, this problem is a variation of a shortest path on a grid, making Dijkstra's algorithm a natural choice. The key twist is that the cost of movement alternates, and there's a move time constraint for entering rooms. To handle the alternating cost, our Dijkstra state had to include not just location and time, but also the number of moves made so far, or at least its parity. And the critical interpretation for move time was that it's the earliest you can initiate your travel towards cell, or a comma j. The actual arrival then depends on this initiation time, plus the specific cost of that leg of the journey. Hope that breakdown made sense and helped you understand how to tackle this problem. If it did, feel free to hit that like button, subscribe for more Leetcode explanations, or drop a comment if you have any questions or alternative approaches. And hey, if you're feeling extra generous, there's always the Boba Fund. Keep practicing, keep coding, and I'll catch you in the next one. Bye for now.